what we described a couple of classes back is that if you have a bounded operator f, then I can express it in terms of the displacement operators trace of f d of alpha. So, this is displacement operator, then d of minus alpha, right. This is what we have described. Now, this is not a very good representation in order to take care of and as a result, if I take a density matrix and take the average value with respect to this operator, this will be alpha belonging to C, this square alpha, trace of f d alpha, then trace of rho d minus alpha. Okay. So, as I said, this is not a good representation in order to so this is so one thing is important is that here you see that this is d alpha and this is d minus alpha, but this is, as I said, this is not a good representation in order to capture all the phase space distribution functions corresponding to different values of S. Okay. And as a result, what one can consider is a Fourier transform. So, before that you take a modified operator which is
d alpha comma s.
Yeah, this is not d alpha comma s, s is 0 here. So, this corresponds to s is equal to 0. Okay.
So, I mean if you want a way to represent arbitrary function in terms of arbitrary s,
Yes,
we should start with arbitrary s, right?
that is what. So, what you can do is you can use d alpha s, which is e to the power s mod alpha square by 2 times d of alpha, where both alpha and s are complex numbers. Okay. And then you can of course try to express things like here trace of rho f is equal to 1 upon pi alpha belonging to C d square alpha trace of f d of alpha s, and now it should be little bit careful. So, this will be rho d of minus alpha and minus s, so that this factor will get cancelled. Okay. Right. Yeah. So, basically it tells you that this you may consider as a weight function corresponding to the density operator rho, and this as a weight function corresponding to the operator f. So, in order to calculate this average value, you need the product of these two weight functions and then integrate it out. Okay. Now, the problem is that I mean, in order to consider this, what we need to show is that can I write from here, that is the question, for any bounded operator can I write it in the following form: trace of f d of alpha s and then d of minus alpha minus s. So, of course, this factor will get cancelled, that is not an issue, but the question is that whether such an expression exists and when can it exist. Basically, when I can express any bounded operator as a linear superposition of this modified displacement operator, and for that what we need is a kind of yeah. So, what we need is a kind of this kind of transformation. So, basically what we need is alpha s dagger d of beta t. Okay. So, we need to see how does it look like. So, this is what will be this. So, this is trace of e to the power s mod alpha square by 2 star of this, then d of minus alpha, maybe I will just write this one, e to the power t mod beta square by 2 into d of minus alpha d of beta. Okay. And this you can figure out, because the star of this means what? So, this is exponential of this is t plus a star, right? Oh, not t plus a star, sorry, this is a star mod alpha square by 2 t mod beta square by 2 multiplied by trace of d of minus alpha d of beta. Okay. And d of minus alpha, this means that sorry, yeah, but some factor is there. I think this is so let me write it first. So, this is exponential a star mod alpha square by 2 plus t mod beta square by 2, and then this will be minus alpha beta star plus alpha star beta into trace of then this is d of beta minus alpha. Okay. And this is pi times exponential of a star mod alpha square by 2 plus t mod beta square by 2 minus alpha beta star plus alpha star beta, and then multiplied by delta 2 of alpha minus beta. So, this is the delta function. Okay. So, basically what you will have is pi times exponential of this is t plus a star mod alpha square by 2, and then this will get cancelled, delta 2 of alpha minus beta. Okay. Is that correct? Isn't it? Because this is a delta function. So, you see that this value is not just pi times delta function, you have this factor, and therefore, I cannot say that this is kind of orthogonal or orthonormal. Okay. So, what I need to, so therefore, to make it a finite quantity, what I need is a real part of t plus a star has to be negative, otherwise it does not make sense. Okay. Oh yeah, so this has to be the case, but even then this is not actually 1. Okay. So, I cannot say that this will form an orthonormal basis. Okay. This will form orthonormal basis provided I take this to be 0, t plus a star to be 0. Okay. So, this shows that these modified displacement operators are not, this will not form a good orthonormal basis, and as a result we should look for something else. Okay. And this something else is what we introduced earlier, is the Fourier transform of this modified displacement operator. Okay. So, this is t of alpha s is equal to 1 upon pi beta belonging to C d square beta exponential of alpha beta star minus alpha star beta. So, this is the complex Fourier transform of d of beta s. Okay. So, this is your new set of operators, right, and and you can prove several properties for this. So, this we have proved earlier that. So, now you can of course express again any bounded operator as of course you will have to figure out what does it mean T of alpha is dagger, T of beta t.
In the previous thing, what if we take t plus s star to be real part to be negative, then there is no problem.
Yes, it is not a problem, but ideally we should have it is like a two-dimensional delta function in order to make it to be orthonormal basis, okay. But that is not the case, right. That will be the case if you take a star plus t equal to 0 or at least real part of t a star plus t is 0, okay. But that is not always the case. Anyway, so this you can figure out what will be this one, we will come back to this later, but you will see that of course depending upon the choice of s and t, this will satisfy this orthogonality condition, and you can again express things. So, basically what we will do is we will take this basis. So, f bounded operator, I will assume that I can express it, in fact you can d square alpha trace of f t of alpha s and then t of alpha minus s, okay. So, this is what we will have, okay. I mean this two will give rise to this thing that okay. So, yeah, so these two will give rise to. So, this is basically your weight function for f, and if I now take trace of for any density matrix 1 upon pi, I mean generally we do the opposite one, we take this as minus and this as plus, okay. So, this I call weight function. So, this is generally written as alpha minus s, okay, and this one alpha belonging to C d square alpha, this f of alpha minus s times this is W rho of alpha s. And what is W rho of alpha s? W rho of alpha s is equal to okay, either you can take this 1 upon pi inside. So, then it should be, maybe I will take this 1 upon pi inside, okay. So, then it is what is this? So, this will be 1 upon pi trace of rho t of alpha s, okay. So, this is my definition of. So, this is weight function for, you can say this is weight function of rho and this is weight function of f, okay. So, you see that any average value corresponding to a bounded operator can be calculated in terms of this weight function for the operator and weight function for the density matrix, okay, right. And this is what is the most general expression. So, W rho of alpha s is equal to plus 1, this corresponds to, so this is basically the p distribution, okay. Now, one should be careful about this factor, but that is okay. So, there might be some 1 upon pi factor or pi factor that we will figure out. So, then this is basically, so I will write here proportional to alpha star, which is the p distribution function, okay. P distribution corresponds to the normal ordering, s is equal to plus 1, W rho alpha s is equal to 0, this corresponds to the Wigner distribution, which is s is equal to 0, symmetrically ordered. and W rho alpha S is equal to minus 1, that is proportional to the Q function. Okay. So, which is alpha rho alpha by pi, which is the coherent state basis. Okay. So, this is for normal ordering, this is for symmetric ordering, and this is for anti-normal ordering. Okay. Right, and correspondingly you will have this weight function. So, this is important, that if I want to express this average value with respect to symmetric ordering, then I will have to choose S is equal to 0, and you see here this corresponds to symmetric ordering, this also corresponds to symmetric ordering. If I choose S is equal to, so if I choose S is equal to plus 1, which corresponds to the normal ordering, then this has to be anti-normal ordering, and vice versa. If this is anti-normal ordering, this has to be normal ordering. Okay. And this is how all these average value expectation, everything will come in this form. Okay. Of course, there are issues of about convergence of this integral and all that we will talk later, but this is the basic feature. Okay. So, this encapsulates all possible phase space distribution functions. Okay. So, now let us look at this operator T alpha s, which is 1 upon pi. So, which is the Fourier transform of the modified displacement operator, complex Fourier transform. So, now I think we discussed earlier that this can be expressed as something like this, 2 by 1 minus s, then d alpha, then this is s plus 1 by s minus 1 to the power a dagger a d alpha dagger, right. I think this is what we discussed some time back, by associating with the with this operator f lambda is equal to lambda to the power a dagger a. In this case, I think lambda is equal to s plus 1 by s minus 1, something like that. Okay. Right. This is your displacement operator. And now, if I write in the number operator basis, so this will be 2 by 1 minus s, n is equal to 0 to infinity, s plus 1 by s minus 1 to the power n. This is d alpha acting on the Fock state, and then its dagger d alpha acting on Fock is dagger, right. This is what you will have. So, this is a kind of spectral decomposition of this operator, right. So, you can see that so at s is equal to 1, this has singularity, right, at s is equal to 1, and this has singularity means because all the eigenvalues are infinity at s is equal to 1, and therefore, so this operator T of alpha s is equal to plus 1 basically. So, this is basically unbounded operator, and you know that this is required to which one, s is equal to plus 1, yes, this one. Okay. And as a result, this p distribution is basically it will have lots of singularities. Okay. This one. Okay. Now, let us come down from s is equal to plus 1. Of course, so if I take s is equal to 0, so t of alpha s is equal to 0, what will I get? The eigenvalues will be plus 1 and minus 1, right. So, this will be the eigenvalues, right, and then I can of course, so the corresponding distribution function is the Wigner function. Okay. So, this is s is equal to 0. Now, what about the boundedness of this operator? Is it bounded or not? The eigenvalues are plus 1 and minus 1, right. Okay. I mean, yeah, this will be 2 factor. Okay. So, we can forget about 2 factors. So, plus 1 and minus 1, right. So, this is something like a unitary operator.
It's not bounded.
It is not bounded. It is not bounded. Yes, it is not bounded. Yes, it is not bounded. But still, Wigner distribution holds for every density matrices. So, this is a well behaved function. We will see that this one. Okay. I mean, still it makes sense. What about alpha t of alpha s is equal to minus 1? S is equal to minus 1, what will be this? This is 0, right. Except for n is equal to 0, is just 1, yes, it is just 1. Okay. So, therefore, so this is, what is this? This is displaced ground state, right. So, this is d of alpha 0. Oh, so basically this is alpha alpha, right. Okay. So, this is of course bounded, and what is the corresponding representation, that is the Q function, okay, which is again bounded, right. So, what you can say is that if I take the real part of S less than equal to 0, equal to 0, of course, there is still we get the Wigner distribution, fine. So, you will have a bounded expression apart from this s is equal to 0 part, that corresponds to Wigner distribution. So, for all other values of s for which real part of s is less than 0, which is negative, this is a well behaved operator, and you can have the corresponding expressions. So, in other words, this function, this is a well behaved function, well behaved in the sense that this is continuous and all those properties are there, uniformly continuous, whatever, for this. I mean, of course, alpha can be anything, alpha can be any number, but if I take real part of s is less than equal to 0, then this is a well behaved function, okay, right. And so, this tells you that starting from s is equal to 0 and going down to minus 1, I mean, you can go even below minus 1, that is okay. So, this I mean weight function corresponding to the density matrix, this is a well behaved function, okay. But if I cross this limit, so if I take real part of s greater than 0, then all these functions are ill behaved function, I mean, this will have singularities and all that. Okay. Okay, good. Generally, I mean, there can be cases where it is not, but generally this is the thing. Okay. right. One more thing. So, when can these eigenvalues be all positive? Positive or 0? Huh?
S is greater than 1.
S is greater than 1.
Yes.
Yes, S is greater than 1. Yes. So, in that case all the eigenvalues are positive, right. Yeah, that will be negative. So, then
There is another solution, and I think less than minus 1. Less than
yeah,
minus 1, yes.
because if S is greater than 1, this is negative. So, I want all the eigenvalues positive, positive or 0. Yeah,
Less than minus 1.
S has to be less than minus 1, right. Okay, I mean I can take also S is equal to minus 1, but that is okay. Yeah, right. So, you see that T of alpha S. Okay. So, okay, so let me call these eigenvalues as, so eigenvalues of T of alpha S, let us call it as E n of S, which is 2 by 1 minus S, then S plus 1 by S minus 1 whole to the power n. So, n is equal to 0, 1, 2, etc. right. So, E n of S is greater than equal to 0 for, what did you say, S is less than minus 1, but S has to be real, right, otherwise it does not make sense. So, S belongs to minus infinity and minus 1 included, because for minus 1 it is 0. Okay. So, S is real, odd powers of n. Yeah. Okay. So, if S is real and less than equal to minus 1, all the eigenvalues are non negative. Okay. Right. And what about, so this is number 1. Number 2, trace of T of alpha S. So, this is basically the 2 by 1 minus S, sum over n is equal to 0 to infinity, S plus 1 by S minus 1 whole to the power n, is not it? That is the trace, right. And what about this? Now, if S is less than minus 1, equal to 1 minus 1, of course, this will be 1, this is 1, right. When S is equal to minus 1, trace of this is 1. Do you agree?
Trace is 1 when S equal minus 1.
Yes.
Because just the ground state.
This is the displaced ground state. Yes. But when S is less than minus 1, S is real and less than minus 1. So, then what is this value? S plus 1 by S minus 1, is it
It's a
geometric series?
and it's always less than bounded by, its mod is bounded by 1, and it keeps on decreasing.
Yeah, but what is the actual value?
Oh, okay, fine.
Okay. So,
Again 1.
so this is 1. So, this is for, of course, S less than minus 1, I mean real S and which is less than minus 1. So, you see that, okay. So, what you see is that when S is less real, so when S lies within this, S is a real number less than equal to minus 1, then this operator, okay, this operator behaves like a density matrix. Is that a correct statement? So, for S belonging to minus infinity and minus 1,
Positive and
Yes. So, alpha S is a density matrix, right, density operator. Okay. Right. But if I go beyond this range, then of course, things will become messy and we do not have much control over that. Okay. Good. Okay. So, now what I will do is I will talk about something called characteristic function, which I introduced earlier also, but now in a more specific way. So, basically what you can introduce is in the generic case, though not just very special cases, you can introduce this. So, I told you that the Wigner function is Fourier transform of characteristic function, right, of a density matrix, but this is true for not just for Wigner function, any S ordered phase space distribution function, this is the case. Okay. So, okay. So, this is the notation, I mean this is the definition, S ordered characteristic function. So, which I will call chi rho beta and then S. Okay. So, this is by definition, this is trace of rho then d of beta S. Remember our characteristic function for symmetric ordered distribution, symmetric ordered characteristic function was trace of rho d of beta, and then if I take the Fourier transform of this, I will get the Wigner function, right. So, the Wigner function of alpha star, this will be 1 upon pi the complex Fourier transform beta belonging to C d square beta exponential of alpha beta star minus alpha star beta of the characteristic function. Okay. And then you can do the inverse Fourier transform also. So, you can do chi rho S beta is equal to 1 upon pi alpha belonging to C d square alpha exponential of alpha star beta minus alpha beta star, then this is Wigner function of alpha star. Okay. So, these are the Fourier transformation connected through complex Fourier transform. Same thing we will see here in the generic case also. So, this you know that this is because I know the definition. So, this is S mod beta square by 2 into characteristic function corresponding to the symmetric ordering, right. Okay. Okay. And so, what you can do is basically now you can write the S ordered phase space distribution function, which is the complex Fourier transform of Okay. So, this is the complex Fourier transform of the S ordered characteristic function, and thereby you can also write taking the inverse Fourier transform this now this is alpha d square alpha exponential of alpha star beta minus alpha beta star. This is this S ordered distribution function. Okay, right. So, this is exactly what we can figure out. Okay, and yeah, so this is your definition. Okay, so you can have all these properties through this, that because we know that the symmetric ordered characteristic function is less than equal to 1 for all beta belonging to. Okay. So, therefore, you can figure out what will be the magnitude of this, bound on magnitude of this. Okay. Right. So, this is basically a, because this is a continuous function, you can show that, therefore, this will be also a continuous function of beta, and for S it is kind of entire function. Okay. So, yes, so this is these are all characteristic functions, and from using that characteristic function you can define your distribution functions also. Okay. Right. Now, I discussed here what are the eigenvalues of these operators, okay, provided S lies within this, okay, because these are, then it will be a density matrix. So, then if I look at these, this I have not written actually, yeah. So, yeah, what about this function? So, this is I discussed maybe somewhere sometime week. So, this one, this is the phase space distribution function. So, this is nothing but trace of rho then T of alpha s. Okay. So, so simple. Okay. Right. Yeah. So, this is the expression, this is for characteristic function, and this is because characteristic function, from here you see that if you express it as a Fourier transform of the displacement modified displacement operator, this is the characteristic function that you get. Okay. Right. So, now if I use the property that this T of alpha s is a density matrix for real s less than equal to 1 minus 1, then you can show that these W rho of alpha s, okay, which is trace of rho and T of alpha s. Okay. So, okay. So, what? So, this is basically expectation value of a density matrix with respect to a state, right. So, what is the maximum it can have? Well, what is the maximum eigenvalue this operator can have? So, here of course, I have chosen S belonging to minus infinity and minus 1. Okay. So, S is a real. So, what is the maximum eigenvalue it can have?
So I think 1, yeah, 1, because trace is 1 and all are positive.
No, you should look at here, all are positive, fine, but what is the maximum eigenvalue here it can have?
Yeah, 1 only.
For given S,
S less than minus 1.
yeah, that is true.
So all values are positive and they sum to 1. So
Yeah, but what is the, so this operator, what is the maximum eigenvalue it can have?
as a function of S.
2 by 1 minus s, yes, isn't it?
Yeah, as a function of S.
Yes, 2 by 1 minus s. So, therefore, this quantity is less than equal to 2 by 1 minus s. Is that correct? I mean, of course, for s is equal to minus 1, no, s is equal to, here, s is equal to minus 1 also, this is fine here. Okay.
But this need not be the case.
Why?
Because it depends on what the rho value of
Rho you can take anything,
yeah
any density matrix you take.
yeah. So it will maximize if rho is exactly the
Yeah,
point
if
at which-
rho is the corresponding eigenvector, then this is 2 by 1 minus s.
Otherwise, it will not.
Otherwise, it will be less than this, right? Okay, right. And when can I say that this value is greater than equal to 0? This is a density matrix. I mean, this is an operator, positive operator. I mean, yeah, positive semi-definite operator.
So you are asking condition S.
Yes. So, for what values of s? So, I consider s to be within this. Okay, do not go beyond this, because otherwise it will not be density matrix. So, within this s, this operator is positive semi-definite.
Yeah. So same range.
So, therefore, the always non-negative, right? Right. So, you see that, and this is independent of alpha, whatever alpha you choose, it does not matter. This distribution function is it lies between 0 and 2 by 1 minus s, provided I choose s within this. Okay, right? And this is particularly true if you choose yeah, of course, s is equal to minus 1, what happens? Yeah, s is equal to minus 1 corresponds to the anti-normal ordering, and that is the q function, and which is, we know that this is always non-negative. Okay. Okay, good. And you can also show that this is a well behaved function actually for all alpha, and it is what is known as uniformly continuous for real part of s is less than equal to 0, but that is okay. I mean, we do not have to bother much about that. So, anyway, in fact, you can show that even if you go beyond this, if you go beyond this range, so what you can show is that the magnitude of rho alpha s is less than equal to 2 by magnitude of 1 minus s for real part of s less than equal to 0. Okay. So, this is more general than this. Okay. And also this is true that 1 upon pi alpha belonging to C d square alpha s mod square. So, this is less than equal to 1. So, basically this is a square integrable function for real part of s is less than equal to 0. So, this is even more general. Okay. So, if real part of s is less than, so basically for this range what we talked about, this function Wigner function, I mean not Wigner function, phase space distribution function, this is a square integrable function, this is bounded and all that. Okay. In fact, you can also show that this is real for, yes. So, let me, that of course is required. What about this maybe let me erase this part. Okay. Yes.
I mean, eventually, this paper came in 70s.
Yes.
At late 60s. So, I mean, for s is equal to plus 1, minus 1 and 0, these were known at that time. Were other value is also studied as a tool to study?
Yes, yes. I mean, but I mean the for physically motivated examples, other values of S are not that important. Okay. So, the other values of S are important for connecting different distribution functions, different S ordered distribution functions.
So these things were not studied
No, before that it was not studied.
after this.
After this, well, some people have used this S ordered distribution function to calculate things, but for particular physical system, other than these +1, 0 and -1 values, nothing important is required. Okay. But this is important for connecting things. So, this is you can think of it in the same way we talk about the pictures in quantum theory, like Dirac picture, interaction picture, then Schrodinger picture, Heisenberg picture. So, all of them are related through this expectation value. Here also the same thing. Okay. Okay. So, what important is this yeah. So, maybe you can figure out what about the complex complex conjugate of this. So, this is what is this? This is trace of rho d of alpha s, not alpha, sorry, t of alpha s, right? T of alpha s, right? Okay. And this is trace of rho t of alpha a star. So, if you recall the definition of t of alpha s, this is, and because rho dagger is rho. So, this is right, and this is your w rho alpha a star. Okay. So, therefore, this is real for real S. Okay. So, whenever I take S to be real, then the space space distribution function is real, otherwise not. So, fine. So, I introduce this Wigner function, I mean the S ordered Wigner S ordered phase space distribution function, then the S ordered characteristic function, then their relation, and okay. So, now this last thing, which again I am not going into the details, is that in order to connect, how will I connect, let us say w rho of alpha s and w rho of beta t, okay, because this is what we should do, right. So, how to do that? Now, this is something which yeah, so which is okay, it is a bit tricky, but let us see how to do that. Okay. Okay. So, this is what I want to connect. Okay. So, how to connect these two, right, and this is once I know the connection, I can figure out how these different distribution functions are related. Okay. So, S alpha s, by definition this is trace of rho then t of alpha s. This is my definition. For the timing I am not assuming that S has to be real and all that, that is okay, that will come later. Okay, good. So, now if you look at t of alpha s, this is being an operator. Okay. In principle I can express it in terms of t of beta t also. Okay. So, 1 upon pi beta belonging to C d square beta trace of T of alpha s, then T of beta minus T, and then T of beta T. This I told you, for any operator I can do this thing, right, okay, in terms of this these operators. Okay. So, now this we have not done, but I will just write the result, because you know what is this trace of d of alpha and d of beta. Okay. So, therefore, you can also figure out what is alpha s and d of beta, let us say t. This also you can figure out trace of this, and from there you, if you take Fourier transform correspondingly, you can figure out these two also. Okay. So, I will just write the result for you. Is that clear? I mean, you will have to take the Fourier transform of this and Fourier transform of this separately to get the trace of this. Okay. So, what you can figure out is this is 1 upon pi into 2 by t minus s beta belonging to C d square beta exponential of minus 2 alpha minus beta square divided by t minus s multiplied by trace of rho t of beta t for real part of t greater than real part of s. If this is not the case, you cannot have this form. In fact, if this is not the case, then this will be divergent, okay, isn't it? If real part of t is greater less than or equal to real part of s, then this will be divergent. Okay. So, you need these conditions, right. So, now using this, you use here. So, what you will get from there, that alpha s is equal to 1 upon pi, then 2 by t minus s beta belonging to C t square beta exponential of minus 2 mod alpha minus beta square divided by t minus s into w rho beta t, provided real part of t is greater than real part of s. Yes, is that clear? Basically, you need to use this definition. So, you see that this phase space distribution function is connected to this phase space distribution function through such relation, provided this real part of t is greater than real part of s. Otherwise, of course, it does not make sense. Okay. Right. So, what is going on here? So, if real part of t is greater than real part of s, then you see, if this is a badly behaved phase space distribution function, you have a Gaussian smoothing here, okay, to make it well behaved. So, therefore, this is well behaved function. So, you see that as I keep on decreasing real part of s, I will get better and better behaved phase space distribution function. Is that clear? Okay. So, now if I take the specific examples of normal ordering, anti-normal ordering, etc., then you can see that let us say s is equal to 0 case, which is the Wigner distribution. So, w rho alpha alpha star, which is my Wigner distribution function. Okay. So, then I take s is equal to 0 and t is equal to t is equal to plus 1, let us say, right. So, then what will happen? So, then this condition is satisfied, real part of t is greater than real part of s, right, and then this is what is this? This is t is 1, s is 0. So, 2 by pi, yes, yeah. So, this will be basically 2 times beta belonging to C d square beta exponential of minus 2 mod alpha minus beta square p rho of beta beta star. Why p rho? Because this corresponds to t is equal to plus 1, which is the Glauber-Sudarshan p distribution. So, you see that Wigner function of the density matrix can be obtained by Gaussian smoothing of the p distribution function, right. Okay. Let us say s is equal to minus 1 and t is equal to plus 1. So, then you will have s is equal to minus 1 means the q function alpha star. So, if you do it, what you will get is again beta belonging to C d square beta exponential of minus alpha minus beta square, then p rho of beta beta star. So, this is for, so this is again Gaussian smoothing of the p distribution to get q distribution, but look at here, there is some exponential, there is some factor, here it is 2, here it is 1, right. And next we take s is equal to minus 1 and t is equal to 0. See, all these are satisfying this condition, real part of t is greater than real part of s. Okay. No, is that the case? Sorry, s is equal to minus 1, sorry, yeah, real part of t is greater than real part of s. So, this will tell you again this is q of alpha alpha star, but this time it will be expressed as 2 by pi beta belonging to C d square beta exponential of minus 2 alpha minus beta square, then w rho of beta beta star. So, again this is a Gaussian smoothing of Wigner function. Okay. So, the q function is a Gaussian smoothing of p function, it is also a Gaussian smoothing of Wigner function, but the factor is different, okay, because this is smaller than this quantity. Okay. Right. So, okay. Now, you can ask what about the converse relation? I mean, so basically can I express this in terms of Wigner function and all that? And from here you can realize that those expressions will not be convergent in general. Okay. You can have, but those expressions are not very useful expressions. But anyway, so once I have this relation, in principle I can figure out what are the relations, provided this condition is satisfied. Okay. Is that clear? Okay. Yes.
Yeah. So, you can write a convergent function in terms of a divergent function, but with Gaussian smoothing.
Yes, because this is the Gaussian smoothing is the one which helps you. Okay, good. And finally, so this is fine. I will just write for you these so for a density matrix, this is the, so this corresponds to s is equal to minus 1 alpha alpha star, this is equal to trace of it should be 1 upon pi trace of rho p of alpha minus 1, or actually for Wigner function only you do not have this 1 upon pi factor, for other things you will have. Okay. Anyway, so then you can also write this rho as as a kind of inverse transformation. So, alpha belonging to C d square alpha q rho alpha alpha star, then P of alpha plus 1. So, in terms of Q function you can express your density matrix like this. Okay. Similarly, S is equal to plus 1, this is 2, P of rho alpha alpha star is equal to 1 upon pi trace of rho T of alpha and plus 1. Okay. So, in this case you can write rho as alpha belonging to C d square alpha P rho of alpha alpha star, and then T of alpha minus 1, and this T of alpha minus 1 is nothing but projection on alpha. Okay. And then S is equal to 0. So, this is W rho of alpha alpha star, this is equal to. So, here you see you do not have this 1 upon pi factor trace of rho T of alpha 0, this 1 upon pi factor is not there, and here you can write rho kind of inverse transformation is, but this 1 upon pi factor is now here. So, this will get compensated, whether you take 1 upon pi factor here or 1 upon pi factor here, this will basically, this is the rule of the game. So, this is alpha belonging to C d square alpha W rho alpha alpha star, then T of alpha 0. Okay. So, so you see that given rho you can figure out these distribution functions, or given the distribution functions you can figure out your density matrix, you can. Okay. So, and this is kind of equivalent in the sense that, for example, if I know my density matrix, I will get to know my Wigner function, okay, at every value of alpha and alpha star. On the other hand, by some means, if I can figure out what is the Wigner function for all values of alpha, then I can figure out the density matrix. Okay. So, this is what is known. So, basically it tells you that this is an equivalent representation, everything here. This is an equivalent representation of your density matrix. Either you can work with density matrices operators, or you can work with the phase space distribution function. Okay. In fact, there is something called tomography. So, where you want to know your state by performing measurement, okay, of different observables. So, you can similarly do the tomography by figuring out what is your Wigner function. Okay. So, for example, if I have Wigner function which is a Gaussian, for example, and it need not be always Gaussian. So, let us say I take the Wigner function of, let us say this is rho is equal to the alpha alpha. Okay. So, this is a, or let us say beta beta. Okay. So, this is alpha alpha star. Okay. So, this is actually you can write it also in terms of these quadrature variables x p, right. So, if I, so this will be basically a Gaussian function. Okay. So, this is some factor for normalization exponential of again some negative factor of, this is x minus real part of beta, or maybe square root of real part of beta whole square minus some factor p minus imaginary part of beta whole square, something like this. Okay. So, this is your Wigner function, this normalization factor will be there. So, this is a Gaussian function. So, if I plot, so this is my x and this is p, and this is my Wigner function. So, it looks like, maybe it will be a circle or ellipse depending upon these factors. So, it will be something like this. okay, no, it is a displaced one. So, I should write here. Okay. So, this is your square root of real part of beta and square root of imaginary part of beta. So, basically you will have a maybe circle or ellipse with center at this, and then it is a kind of Gaussian, okay, on this, right. And so, how will you get that Gaussian function? So, let us say I take slices of this. So, let us say I take a cut of this parallel to this x, this is z, let us say. So, x z plane, right. So, it will be something like this. So, maybe I do not know, something like, so this is the curve that you will get, and now you rotate it by that means you take other slices, then you can reconstruct these surface, okay, and that is what is known as tomography. So, once you get this surface, you know the Wigner function, and therefore, you know the density matrix also. I mean, this is I am giving one example, but this is true for any Wigner function. Okay. And taking this cut means, doing measurement along some direction. Okay. So, this is basically on the xp plane you measure along some direction. Okay. So, this is some direction, maybe lambda x plus mu p, some direction. So, this is your rotated quadrature variable. So, you perform measurement of this observable, then you will get this curve. Okay. Is that clear? Okay. What is the time now? We still have time. Okay, good. So, now let me just give some examples, and then it is the end of the story. Okay. So, let me give you some examples. Okay. Yeah. Okay. So, this T of alpha minus 1. So, this you know that this is your projection on coherent state, right. This one is a projection on coherent state. Okay. So, this is one extreme. For any alpha, for s is equal to minus 1, this is your projection on coherent state. Okay. This is a well behaved operator and all that. And now I take t is equal to, now I fix 0. So, this is alpha is equal to, so this is s is equal to minus 1, and now alpha is equal to 0 and s can be anything.
So, Professor Ghosh?
Yes.
The camera has not moved to the other board. Now it's fine. Yes.
Okay. Okay. Good. Can you see me now?
Yes, we can see you and the board. Thank you.
Thank you. Okay. 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 So, now I take the other extreme. So, this is one extreme, the other extreme is this, right. Now, this one, what is this? This is 2 by 1 minus s d of alpha is equal to 0, then minus 1 to the power a dagger a d of minus alpha, I mean basically alpha is equal to 0 dagger, right. This is what we have. Okay. Now, d of alpha is equal to 0 is identity. So, this is 2 by 1 minus s, oh no, sorry, this is not minus 1, s plus 1 by s minus 1, sorry, yeah. So, this is 2, so therefore, this is equal to s plus 1 by s minus 1 dagger a, right. and this is nothing but n is equal to 0 to infinity 2 by 1 minus s. This is s plus 1 by s minus 1 whole to the power n. This is n n. Okay, right? Okay, good. And as we know that, I mean, this is a density matrix operator for s belonging to minus infinity and minus 1 including, right. This is what we discussed. Okay. So, as a result, all the eigenvalues of this operator are basically less than equal to 1, right, all the eigenvalues. And this you can see that this is something like a thermal state, right. And what is that thermal state? Basically, this is, you can write it as 1 upon the average photon number, then n is equal to 0 to infinity n bar divided by n bar plus 1 whole to the power n, this is n n, and where this n bar is equal to minus half, this is s plus 1. You see, because s is less than equal to minus 1. So, s plus 1 is negative, and therefore, yeah. So, this is what you will have. Okay. This is your, this thermal state distribution. Okay. This is the average photon number, right. Okay. I mean, you can now figure out what will be the corresponding. So, basically this will be, this will correspond to something like it minus beta h divided by the partition function. Okay. Okay. So, this is what you will have. So, you can figure out from there what will be n bar. So, n bar has a correspondence with the temperature. Okay. And now, here it is this parameter s. Okay. Right. So, what you see is that this is a pure state and this is a mixed state, right, because if I take s to be strictly less than minus 1, all these eigenvalues are positive and therefore, this is a mixed state. Okay. So, if I now look at this T of alpha and T, okay, or alpha and S if you want, T of alpha and S. So, this is what? This is basically you have D of alpha, then T of 0 and S and D of minus alpha. Is that a correct statement? Right, because there is no difference in the eigenvalues, only difference is in the eigenvectors. Okay. Right. Okay, good. And then you can write in terms of what will be the eigenvalues, eigenvectors, etc. So, basically this is, you see that this is this is 1 upon n bar plus 1, n is equal to 0 to infinity, n bar by n bar plus 1 whole to the power n, d of alpha n n d of minus alpha. So, this you can say is the displaced thermal state. Okay. This corresponds to. Okay. And now, if you want to calculate the Wigner function, I mean the distribution function, not necessarily Wigner function, alpha s for this s value, So, this is, as we know that this is trace of rho, then T of alpha s. Now, this is trace of this rho means this rho, this T of alpha s. Okay. So, I should use some different notation, maybe I will call this as T of beta t. Okay. This is my T of beta t. Okay. Is that clear? I mean, basically I am taking this one. See, this is my definition. I have no restriction on alpha and s here. So, which is given by trace of rho and T of alpha s. Now, I am taking this rho itself as this one, which is beta and t, where of course, this t is it satisfies this condition. So, of course, here t belonging to minus infinity minus 1. This is of course true. Okay. Right. So, now if you again you can figure out from here. So, this is your expression for okay. So, this is your expression for yeah. So, this is your expression for T of beta t, and then if you use. So, again I am not going into the details. So, basically what you will have is this one. This is 2 by 2 n bar plus 1 minus s into exponential of minus 2 alpha minus beta whole square divided by 2 n bar plus 1 minus s. Okay. And yeah, now you may say that where is this t, right? Where is this t? There is no t, but you see that this t, this n bar is minus half t plus 1, okay, according to this thing. Okay. So, basically this is your n bar that you have used. Okay. So, now this is your distribution function, s order distribution function, and from here you can figure out what will be the forms of. So, let me erase this part. So, this calculation you can do, it is not difficult, you can figure out from here. So, now what you can see is that, yeah. So, let me write it down. So, this W rho of alpha and s is equal to plus 1. So, which is your P rho, it is not P rho, pi times P rho of alpha alpha star. So, this is the Wigner function. So, this will be equal to 1 upon n bar yeah 1 upon n bar, then exponential of minus alpha minus, yeah, this is a bit complicated thing, what shall I do? This is a bit tricky issue. So, what I am doing here is the Q function, I am writing the P function for this density matrix. Okay. P function for this thermal state, that is what I am writing here. Okay. So, this rho is your T of beta and T. Okay. This is for the thermal state. Is that clear? I mean, I should have used some other notation. So, okay. So, this T of beta T is your rho thermal corresponding to this average photon number n is equal to minus half T plus 1. Is that clear? So, this means that this is your displaced. So, what is that? Yeah, this is displaced rho thermal. Okay. So, this is your displaced thermal state. Okay. So, I should write like this. So, this is your d of beta, then rho thermal corresponding to n bar is equal to minus half T plus 1, then d of minus beta. So, that is my state. So, this is the displaced thermal state, right. Okay. So, that is, so I am taking rho as this. Okay. So, maybe you can write here rho thermal, yeah, anyway. So, then it will be clear. So, this is alpha minus beta. So, this beta comes from this displaced one. Okay. So, alpha minus beta square divided by n bar. So, you see that this is a Gaussian. Okay. Beta is fixed, but as a function of alpha this is Gaussian. So, the p function, p distribution function of a thermal state is Gaussian. Okay. Is that clear? Okay, good. What about this Wigner function alpha alpha star, which is rho thermal of alpha s is equal to 0. So, this if you calculate, this will be 1 by n bar plus half exponential of minus alpha minus beta whole square divided by n bar plus half. Again it is a thermal, I mean thermal means, sorry, it is a Gaussian one. Okay. And finally, W, so this is 1, and then this is q of rho of alpha alpha star. Okay. So, maybe I will just write this is equal to 1 upon pi, this is 1 upon pi W. See, there is some problem with these factors. Okay. So, I think in this paper and what unit I am using, there is a problem in this factor 1 upon pi, but that can be figured out, it is not difficult. Okay. So, so this is your alpha is, and then s is equal to minus 1, and this is equal to 1 upon pi into 1 by n bar plus 1 exponential of minus alpha minus beta whole square divided by n bar plus 1. Okay. Again this is Gaussian. So, you see that for thermal state, p distribution, Wigner distribution, q distribution, all of them are Gaussian, except for you have this change in this width of the Gaussian, right. Other than this is Gaussian. So, thermal distribution, which is a completely classical distribution which you can think of, all these functions, distribution functions are well behaved, okay, right. And it is, I would say, the only state for which all these functions are well behaved. Even for coherent state, we know that p function is a delta function. Okay. So, if I take rho is equal to alpha alpha, then the p function for this alpha alpha, let us say beta beta star, this is some delta function alpha minus beta. So, this is also not well behaved function. So, except for this thermal state, all the functions generally are ill behaved function, okay, right. And okay. So, what I would suggest is that you can figure out the, okay. So, with this, what is the time now, I will just, so this you can figure out. I am not going to write the solution, but this is for you to figure out. So, I have talked about the Wigner function q distribution, p distribution for for a thermostat. So, what you can figure out, this is equal to, let us say, a number state. What is this? This is alpha alpha star. Yeah, I'll just come. Yeah, I'll just finish. Yeah, sure. And then this is a W rho n is alpha alpha star. So, these are not all well behaved function, but you can figure out what will be their form. So, for these Fock states, whatever be the value of n, and similarly you can figure out for rho is equal to alpha, p rho is equal to alpha coherent state, and w rho is equal to alpha. So, Fock states, coherent states, and then thermostat I already described. And one more thing you can figure out, but that we will do later also. So, this is called squeeze vacuum state. So, rho is equal to SR 0 0 SR dagger, where SR is equal to exponential of R a square minus a dagger square. R is greater than or equal to 0. This is a number. So, this is called squeeze vacuum state. Okay. So, for this also you can try to figure out what is rho alpha alpha star, q rho alpha alpha star, and p rho alpha alpha star. This is a very important state. It has all this non-classical behavior, and we will see that. Okay. So, at least some of this you should try. So, in my next class I will start with this the Gaussian distribution, Gaussian phase space distribution, and then we will talk about the entanglement issue of Gaussian states. Okay.